Okay, this video is on the periodic table of elements. It's basically its construction and trends. I'm going to assume that most viewers of this video have an understanding of what the periodic table of elements is and how it was first founded by Mendeleev. So we're not going to go into too much detail of the history, but we will talk about how this periodic table is set up and constructed. Okay, so you have a periodic table in front of you, and the reason why I like this particular periodic table for is colorful. It's easy to look at. But the colors represent different types of groupings of elements, right? And some of the colors represent metals, some of the colors represent alkali earth metals, alkali metals. These are all different types of groupings of metals and nonmetals. And by looking at the periodic table, you can tell where these types of groupings are just by the color. But you can also don't need to have the colors if you understand how the periodic table is set up. So the first thing we are going to understand is that our periodic table has both these things called up and down and across, or groups and periods. And our groups are the columns in the periodic table. So groups equals columns. And let's look at here. Here's one particular group, and here's another group. Here's another group here, another group here, etc., etc. And anytime that they're up and down, it's a group. Groups are also called families, right? Now, the other flip side is that the periods, right, are called or the rows, or the horizontal rows, right? And they would be located here. So here's period 1. Here's period 2, period 3, and period 4, etc., etc. And the periods represent the number of energy levels of the electrons. So period 1 only has one energy level of electrons. Period 2 has 2 energy levels of electrons. Period 3, 3 energies, etc., etc. So by knowing what period your element is and what group your element is, you can tell me what energy levels the electrons are in, and also how many valence electrons you have. So let's go back to the valence electrons per second here. So anything in this column here, which we're calling the alkali metals, except for the hydrogen, is going to have 1 valence electrons. This is going to have 2 valence electrons. We're going to skip over the transition metals, and we're going to go to this group here, aluminum boron. That's going to have 3 valence electrons. This has 4, 5, 6, etc., etc., until you get to the noble gases, which have a complete shell, which have 8 valence electrons. Okay, so that's basically how it's set up. So now let's couple more quick things about the periodic table as far as groups and periods and families and rows. And let's talk about each one of these things. So this column here is going to be called our alkali metals, except for hydrogen. Hydrogen is just a unique thing, and it's categorized over here because generally it loses an electron more so than it gains an electron, so that's why it's in this column. But it really doesn't have any metallic properties. Our second column, or second group, is called the alkali earth metals. And they have 2 valence electrons, right? And then we go over to group 3, or actually it's group 13. Group 13, and that's going to be aluminum, gallium. They're going to have 3 valence electrons, and this has 4 valence electrons, etc., etc., all the way across until you have 8 here. Now we're going to do one more thing while I'm here, and I'm going to draw in this thing called the staircase. And you've seen some periodic tables have a staircase, and we're going to draw in our staircase right now, and to show you what it means by that. There's a staircase that starts right below boron, and then travels down just like a regular staircase all the way down to the end here. And the staircase separates what we're going to be calling metals and non-metal elements, right? So the staircase, so to the left of the staircase, so anything that's to this side, we're going to classify as a metal. and then anything to this side of the staircase we're going to classify as a nonmetal. Okay, so those the staircase represents the defining boundary between metal and nonmetal. And when a metal and nonmetal bond, they usually form an ionic bond. And when two nonmetals bond, they form typically a covalent bond. Right. Now there is a unique set of elements that are right along the staircase, and we're going to circle them right now. And those are called the metalloids. Right. And the metalloids actually have both metallic and non-metallic properties, depending on the environment that they bond are in. Sometimes, for example, silicon acts as a nonmetal, but most of the time it acts as a metal. Arsenic mostly acts as a nonmetal, but sometimes it acts as a metal. So generally, if you're on the left-hand side of the staircase, as far as the metalloids, you're more metallic-like. And if you're on the right-hand side of the staircase, you're more non-metallic-like. And the nice thing about the metalloids is they have a variety of neat properties that they can be taken advantage of that typically a metal or non-metal doesn't have. So they can, depending on the conditions, for example, silicon is used in the electronics industry a lot because it has both insulating and conducting power depending on how much energy you put into it. Right? So they use it a lot for transistors and chips. Okay, so that's basically the understanding of the breakdown of how the periodic table is set up. Let's talk about a little bit more about the trends that go on with the periodic table. Okay, our first trend that we do with the periodic table is the atomic mass and the atomic number. And generally, what happens is the atomic mass is going to increase as you go both across a period, this way, and down a group this way. And that makes sense because as you add more protons and neutrons to the element, which is what you're doing when you're every time you go across a period from this way to this way and keep going down, you're adding one more proton, and not only are you adding one more proton, you're also adding, and sometimes, one more neutron or several more neutrons, which adds to the total mass of the element. And then as you go down in rows, which is going down this way, so you go down the group, which is basically increasing the number of rows, we're adding more and more energy levels, more and more electrons, more and more protons. So everything increases as you go both from top to bottom and from left to right. So the takeaway from here is that as you go down a group and across a period, both atomic number and atomic mass increase. Okay, so the next trend we're going to talk about is about the atomic radius, which is basically the size of the atom for each element. And let's start with just going down a group first, or down a family. It makes sense as you add more and more energy levels and more protons as you go down the group. Right, we're going down the group here. You're going to increase the mass of the element, and therefore, as you add more and more mass and more and more electrons, the number of shells of the electrons increases, and therefore the size of the atom is going to increase. So that makes perfect sense. Where the student and some learned scholars get troubled with is, why does the atomic radius decrease as you go across a period? It doesn't really make intuitive sense at first, right? We're adding more protons, we're adding more electrons, but yet the atomic radius is decreasing. And the reason why is because the electrons, as you add them, are experiencing a higher positive nuclear charge on them than the previous element, and therefore they're getting drawn in more. And let's draw a little diagram of what I mean by that. So let me just draw the diagram. Okay, so I have drawn an atom of lithium here. So this is lithium. And you can see here that there are the two 1s electrons, and then there's the 1 2s electron. And you can see that what we're going to talk about here about shielding and stuff is that the two electrons on the 1s in the 1s orbital here actually partially shield the electron in the 2s orbital from the nucleus, right? And the nucleus has a +3 charge. So let's just write that down here as a +3 charge in the nucleus for lithium, right? And so what happens is these electrons here partially shield the electron in the outer energy level, which in this case is the second energy level. And the electron is slightly the pull on the electron from the nucleus is slightly reduced because we have a little bit of blocking from the nucleus, from the two electrons closest to the nucleus. Now let's draw a carbon atom, or let's draw an oxygen atom. Okay, I've drawn an oxygen atom now with the over here. Here's my oxygen atom over here. And what I can show you now is that you now have a +8 nuclear charge, right? There's 8 protons in that. And it's in the same period as lithium, so we're looking at the same type of energy level. But look what happens now. I have 8 protons in here that are pulling on all 8 electrons, right? And I still get that partial shielding from the 2 inner electrons here. Here's my 2 inner electrons, and they're shielding these outer electrons somewhat. Not as much as they're shielding the one lone electron out here. They actually now have to try and shield 6 electrons. But I have 5 more protons that are now pulling on these outer electrons. Remember, they're all in the same energy level, so they have no more or less energy than the other one in lithium. So they get pulled in farther. And once they get pulled in, because the effective nuclear charge on them is greater than the lithium one, they get pulled in tighter, and therefore the oxygen atom is going to be smaller than the lithium atom. So anytime you're going from in a period, anytime you go from left to right, you're going to experience a decrease in the size of the radius, or the size of the atom, due to an increase in nuclear charge, and the effective charge on the electrons is increased. You have less types of shielding that goes on. As you go down the period, down the group, the energy level, there's more and more shells out here, and therefore it has to get bigger and bigger. Okay, our next one is metal reactivity. And remember what I said about before was where the metals were located, right? And they're located and then this is a rough estimate of where the staircase is. They're going to be on this side of the periodic table, and our non-metals are going to be over here on this side of the periodic table, right? So all our metals are over here, and these are where our non-metals are. So we're looking at for metal reactivity, right? So the metal reactivity. And we're going to define metal reactivity as the ability, or the ease at which ability to lose electrons, right? Because a metal, what it wants to do is it wants to lose electrons to gain a more stable electronic configuration, right? It wants to become more inert-like. It wants to be more halogen-like. And if you're here, the easiest way to do that is to lose electrons and go back into a configuration that looks like a halogen, right? So it wants to lose electrons, right? And therefore, there's a couple of things that are going on. Remember, the metal reactivity, if it wants to lose electrons, as we go from left to right across a period, the desire to lose electrons is reduced, right? So this wants to lose electrons, these want to lose electrons, lose electrons, lose electrons, until you get to about here, And now the tendency is, okay, I don't want to lose electrons anymore. It's easier for me to gain electrons to become more inert like this side than lose all of these electrons to go back this way. So elements like nitrogen, sulfur, bromine, chlorine, fluorine, they're all going to be very low in metal reactivity compared to things like here. So as you go down, as you go across a period, the reactivity of the metal reactivity, or the ability to lose electrons, is decreased. Now, as you go down a group or down a family, right? Remember, we talked about the electron shells of the atom, right? So let's look at lithium again. Lithium had, 2 shells, right? And as we go down, we're going to 3, 4, 5. We go making more and more shells around as we get bigger until we get down to cesium and francium. And let's reduce this here. As you get down further and further, strontium, let's just do that for strontium. As you go down further and further, you have more electron shells, and therefore these electrons are so much more shielded from the nucleus out here that they're easy to release, right? And they're easy to be lost, because there's very little pull from our nucleus in here on here because of all the shielding that's going on in here, right? All the shielding that's going on from these electrons shield these electrons, and these electrons shield these electrons, and everything's shielded until you get down to here, and therefore the pull on this electron to the nucleus is very weak, and therefore it's easy to release, right? And I know for a fact that cesium, francium, all these elements basically do not have are not freestanding. In other words, you cannot find them in nature unbonded, because they basically want to get rid of their electrons. So again, let's just review real quick before we go away from this slide. As you go down a group here, the metal reactivity increases. As you go across a period from left to right, the metal reactivity decreases. Okay, so now you know that the metal reactivity, what the trends are for that. So it's going to be opposite for the non-metal reactivity, because remember, in non-metal reactivity, we want to gain electrons, right? That's the definition of a non-metal reactivity, and therefore remember that if you're on the metal side here, right, our goal is to lose electrons. So therefore, as we go down a period, down a group or family, these elements here, they don't want to gain any electrons. They actually want to just quickly get rid of electrons. So they're going to be very low in non-metal reactivity. And then you have materials over here, fluorine and chlorine, oxygen. They actually want to have electrons. They want to gain electrons so they can be more like these elements here as far as a full stable shell. So therefore their reactivity is going to increase as you go across a period, and very much decrease as you go down a period, right? So that's so if you can understand that the trend is for the metals and non-metals, they're basically opposite of each other. So now we're increasing the ability to gain, or the desire to gain electrons, and then decreasing the desire to gain electrons. Even though lithium still doesn't want to gain electrons, it will gain electrons much more easily than things like francium and cesium. Not that it's going to gain electrons at all. It's just that if you had a relative scale, these are going to be wanted to just basically get rid of electrons so easily that it's almost non-measurable. Whereas lithium, you could have a stable form of lithium by itself before it loses its electrons. Okay, here's our ionization trend, and our ionization energy basically is defined as the energy necessary to remove an electron from the valence shell. Energy to remove E from valence shell. I'm just going to put valence shell there. All right, so how easy is it to remove, how much energy do I need to remove an electron from the valence shell? And if you remember back to our trend so far, these materials here, I mean, they're going to be very easy to remove the electrons from the valence shell because they're already almost out the door anyway, right? They want to get lost anyway. So we know that the ionization energy necessary to remove the electron, or the energy I need to put into an atom to remove its electron, is going to be extremely low here. It's going to be low here too, but very, very low here. And the energy to remove an electron from an element that really wants to gain electrons. So not only do I want the electrons, if you're trying to remove an electron that I want, it's going to be very high energy, right? So these are the highest energy ones, and these are the lowest ones. So we're going to put low here and very high, right? So as you go across a group, across a period, right, this way, the tendency to, or the energy required to remove an electron is going to increase. And then as you want to go down a group, the energy to remove an electron is going to decrease. Okay, so you understand what the ionization energy is for an element or an atom. Let's talk about the electronegativity trend, right? And electronegativity is not something that you measure directly. It's not a measured value. It's a relative value defined sometimes by the Linus-Pauling scale. There's some other scales for electronegativity. But the electronegativity, the definition is the desire to acquire electrons. That's all it is. It's the desire to acquire electrons. So it's how much do I want to acquire electrons relative to another atom on the scale here. So our elements that really want to acquire a lot of electrons, are, you know, in this corner right here, right? And then the elements that don't want to have any electrons, don't want to acquire any types of electrons, the least ones are here, right? So those are the two opposite ends of the spectrum. So these are the least amount, and this are the highest amount, right? So this has the highest desire. These elements have the highest desire to acquire electrons, and these elements have the lowest desire to acquire electrons. So based on that, you can see the trend is, as you go from top to bottom in a group family, the electronegativity is going to decrease, and as you go from left to right across a period, the desire to acquire electrons is going to increase significantly. Now, there's only one caveat to this, and let me just do a quick erase here. There's one area that you have to be cognizant of that kind of dispels or goes against the trend, and I'll tell you why in a second. These elements here, the inert and noble gases, they have zero electronegativity. They don't want any electrons. They have no desire to acquire more electrons because they have all the electrons they want. So the period increases across the scale this way until you get to the end of the halogens and you start to get to the inert family. There is no electronegativity thing for the inert gases, right? So one more quick thing about the electronegativity is, and we're going to erase all this, is that it's a relative scale defined by a bunch of scientists, but Linus-Pauling scale is the one that's generally used, and it assigns fluorine the value of 4, and it assigns things like cesium and francium a value somewhere around 0.7, right? So, and that's probably being generous, but the inert gases are all 0, right? So, so if you can look at it this way, that this one is 4, but neon is 0. So there is a if somebody said to you, what is the which has a more electronegative value, fluorine or neon, the answer is fluorine, even though that neon is further to the right on the periodic table, and that's where the general trend is that goes from left to right. It's going to increase. In this case, the barrier, the stop point, is the inert gases. Excuse me, the inert gas, the transition between a halogen and inert gas. Okay, this table basically sums all the things we just described. So if you have any additional questions, you can come find me. But hopefully this was informative.